The speed of light in a vacuum is 3 times 10 to the 8th meters per second, and it's given the symbol c. But in water, the speed of light is different. It turns out to be 3/4 c. And in fact, in any different medium, the speed of light will be different than in a vacuum. And the index of refraction is given the symbol n, and it's defined as the speed of light in a vacuum divided by the speed of light in any medium. So for example, if the index of refraction for glass was 1.5, that would mean that light is 1.5 times faster in a vacuum than in glass. Now here's how refraction works. Suppose we have water as one medium and air as another. Everything is measured to a normal line, very important. And the incident ray comes to the surface, and water is more dense. It will bend towards the normal, in the more dense medium. That's the refracted ray. Theta 1 is the angle to the normal as the angle of incidence. Theta 2, the angle of refraction. Now there's a very important law you need to know. It's called Snell's law, and last year we actually did an experiment to measure this. N1 sine theta 1 equals N2 sine theta 2. N1 is the refractive index of the air, which also turns out to be 1, very close to the vacuum. And then N2 would be the refractive index in water. So you need to know that relationship very well. Now, when light travels from one medium to another, not only does the velocity change, but the wavelength changes, and the wavelength gets smaller. So in going from a vacuum to another medium, the wavelength changes, but the frequency does not change. Now here's your one-stop, everything you need to know formula. And we can write it like this. Sine theta 1 over sine theta 2 would equal, it's easy to see, N2 over N1. Now look at this. It equals V1 over V2, which equals lambda 1, the wavelength, over lambda 2. Memorize that, know it well. It's sort of your one-stop, everything you need to know, full meal deal for refraction and refractive index. Now one more thing, something called the critical angle. Suppose the incident ray went from water to air. The ray will bend away from the normal. So if I had a larger angle of incidence, theta 2 was larger, what happens is it will now bend farther from the normal when it reaches the air. And if I had an even larger angle of incidence, it will bend even more. There's a critical angle such that when light travels from the water to the air, or water to another medium, it'll go right along the edge, and the angle of refraction would be 90 degrees. That's called the critical angle. And in this case, theta 1 would be 90 degrees. So here's a very simple sample question. What is the critical angle when light travels from glass, N is 1.5, to air, 1.0? So there's Snell's law. And we're going from one medium to another, so we would write down Ng sine theta g is Na sine theta A. In this case, N of the air will be 90 degrees because we want the critical angle. And so we solve for sine theta g, which equals Na sine theta A divided by Ng. And the index of refraction of air is 1, and sine 90 degrees is 1. So we will have 1 times 1, and Ng equals 1.5, and you solve and find the critical angle. There it is, 42 degrees.